In this video, we are going to discuss thermal expansion. So as temperature increases, the volume increases due to an increase in the spacing between atoms. Now, we are going to focus here initially on the linear expansion, so just a change in length. And this change in length is going to be proportional to the change in temperature for small changes in temperature, so something like a change in 100 degrees. Once we get past that, things get a little wonky, but we're not going to talk about that. It's also going to depend upon the original length. So the greater the temperature change, the greater the change in length, the greater the original length, the greater the change. And a constant. And this constant, represented by the Greek letter alpha, is going to be called the coefficient of thermal expansion. And it's going to have units of inverse temperature units, so usually Celsius to the -1 power. And these are found in a table linked in Blackboard from your textbook. And this is going to depend upon the material. Some materials expand more than others due to an increase in temperature. And this is something important to take into account whenever you are designing something that is going to undergo extreme temperature changes. Because there could be a point where the change in length stresses the object so much that it actually breaks. I had this happen to me once. I had a Keurig machine, and of course I forgot to put something underneath of it once I turned it on. So I just grabbed a glass from the dish rack, and it was an actual glass and not a glass designed for hot liquids. And as soon as the hot water started hitting the glass, I could hear this giant crack because the change in temperature had expanded the glass beyond the breaking point of the glass. I've also heard this story from students who have worked as waitstaff, where they're taking a hot glass straight from the industrial dishwasher, trying to put a cold drink in it, and you get compression then, rather than expansion, and the glass shatters. So it matters what that coefficient is and how much the material is going to expand or contract, and that could be a problem if it's beyond the stress limit of the container. And just to point out here, because this is a delta T here, where you're doing temperature final minus temperature initial, as long as both temperatures are in Celsius or both temperatures are in Kelvin, you are fine with this equation. They just have to match. Now we can also do this for more than one dimension. So I'm going to also give you the relationship for the change in volume. So the change in volume is going to equal a different coefficient. So this is going to be the coefficient of volume expansion times the original volume times the change in temperature. So you can do this for both 1 dimensions and 3 dimensions. And I want to point out again that this coefficient and this coefficient are different values. Now I mentioned earlier in this lecture the idea that due to the expansion there is stress on the material. So we're going to learn how to calculate that stress. We would have learned in Physics 151 that stress, and specifically stress due to a force due to tension, so force per area, is going to equal the Young's modulus times the change in length over the original length. So I'm going to rearrange this so that the change in length over the original length, and we're going to label this one tension, because this is going to be due to tensile stress, is going to equal the force per area. Remember, that's the tensile stress. And then we're going to have the Young's modulus in here, and that Young's modulus depends upon the material. And I'm going to take our thermal expansion equation and so this is going to be thermal. And it's going to equal our coefficient times the change in temperature. So this is how much it would expand if it wasn't hindered by the tensile stress that it is under. So we can say here that the amount that it is trying to expand plus the amount of tensile strain that it's being prevented from expanding under is going to sum to 0 because it's trying to expand and it's getting pushed back from whatever it's expanding against. So we're going to sum in our two relationships here. And rearranging, we can calculate the thermal stress that it would be under, at least for a linear relationship. So this is what we refer to as thermal stress.